Hello. In this video I want to take a look at another form of polynomial division called synthetic division. For this form of polynomial division I can only use certain factors as my divisor, namely things of the form x plus or minus k. So this means I could use a divisor such as x plus 2 or x minus 7. What I will not be able to use is anything where my leading coefficient is not 1, such as 3x plus 1 would not work with synthetic division. Also things of higher order or higher degree. X squared minus 9, for example, is not going to work with synthetic division. So let's take a look at what this process is. Synthetic division is different than polynomial long division in that it deals directly and only with the numbers. Here's what I mean. I want the quotient of p of x, which is 2x cubed minus 9x squared plus 14x minus 8, and x minus 3. So what I'm going to do first is take the coefficients of p of x. Now looking at p of x, I can see I have a cubic term, quadratic, linear, and constant. There's nothing missing. I'm not missing an x or an x squared or anything like that. I have all the powers of x. So I will take all of these coefficients, 2, negative 9, 14, and negative 8. I'm going to draw around this. What do I do with my divisor, my x minus 3? Well, what I'm going to do with my divisor, what I really want to use is the root of that divisor. So I set it equal to 0. X minus 3 equals 0 will mean that x is equal to 3. So what I'm going to do is use that 3. Now pay attention to this process. The first thing I'm going to do is take this 2, this first coefficient, and drop it down. Now, what's going to happen in this process, I will be bringing numbers down below this line, and each time I come below the line, I'm going to multiply. I'm going to multiply by this 3. 2 times 3 is 6. My next step is to add negative 9 and 6. Negative 9 plus 6 is negative 3. Now pause for a second. Before I complete this, I'm going to make a note of the process I just followed. The first thing I did, once I got all of my coefficients and my root, was I dropped that leading coefficient. And then the process from there is to successively multiply and add. And I'm going to continue on this way. I will keep multiplying and adding until I'm done. So again, I dropped 2. 2 times 3 is 6. Negative 9 plus 6, adding these two gives me negative 3. Next, I want to multiply again. 3 times negative 3 is negative 9. Adding these two, 14 and negative 9, make positive 5. 3 times 5 is 15. Negative 8 plus 15 is 7. All right. So I followed this process, drop, multiply, add, multiply, add. What do these numbers mean? How does this give me a quotient? Because we know when we divide two polynomials, I should get another polynomial, and we know how to work with the remainder. Well, here's the deal. This was a cubic function. So this down here will represent 1 degree lower a quadratic function. So that was x cubed. This is x squared. This represents the coefficient of an x. This represents a constant. And this last term right here is my remainder. I can think of this, however, it also might make more sense to say remainder constant x and just count up to whatever power term I have at the most. So what we have just determined using this method is the quotient of 2x cubed minus 9x squared plus 14x minus 8, and x minus 3 is 2x squared minus 3x plus 5 plus 7 over, what was my divisor? X minus 3. This is my answer. Once you get used to this process, it's actually quite simple, but you do have to get used to it. Now there are some things to note here. Just before, a remainder of 0 indicates that the divisor is a factor of our polynomial. That did not happen here. I did not get a remainder of 0, so x minus 3 is not a factor of this polynomial. This remainder right here, this 7, well, that is actually related to this problem. What that 7 is what I would get if I substituted my root into this polynomial. 7 is p of 3. You can check this if I actually show my work right here. P of 3 would be 2 times 3 cubed minus 9 times 3 squared plus 14 times 3 minus 8. Simplifying these things, this is 2 times 27 minus 9 times 9 plus 14 times 3 is 42 minus 8. And keep simplifying, this is 54 minus 81 plus 42 minus 8. And I'll leave it to you to check, but if you simplify these, you do actually get 7. Okay. So the remainder is whatever my polynomial is evaluated at the root. The remainder is, I'm going to write p of r, where r stands for root. Okay. So this is why it is sometimes called synthetic substitution. If I wanted to evaluate this polynomial for some other value, such as 5 or negative 9, I could write this whole process out, put my whatever value up here, and when I get to the end, this is what I would get if I evaluated this polynomial. But I digress. More about the division. Let's take a look at some more examples with the actual division. All right, so here, 3x squared, that's a typo, 3x cubed, plus 26x squared plus 51x minus 20 is being divided by x plus 4. All right, so we're going to set this up. The coefficients here are 3, 26, 51, and negative 20. X cubed, x squared, x, and a constant, so everything is fine there. X plus 4, well, the root of x plus 4 is negative 4. And I will again do the same process. Drop, multiply, add, drop, multiply, excuse me, I only dropped once. Multiply, add, until I am done. So I drop the 3 down. I multiply by negative 4 and get negative 12. 26 plus negative 12 is 14. Negative 4 times 14 is negative 56. 51 plus negative 56 gives me negative 5. Negative 4 times negative 5 is positive 20. All right, negative 20 plus 20 is 0. So again, I need to convert this to a polynomial. Now I know right down here, this is my remainder, this is my constant, this is my x term, and this is my x squared term. Okay, so that means that this quotient right here is actually equal to 3x squared plus 14x minus 5. Now again, I got no remainder, which means if I put negative 4 into this polynomial, I would get 0. Now what's also interesting about that is this allows us to factor more. Since the remainder was 0, that means that x plus 4 is a factor of that numerator polynomial 3x cubed plus 26x squared minus 51x, plus 51x minus 20. Where we're going to go with this is eventually I will then be able to factor this entire polynomial because 3x cubed plus 26x squared plus 51x minus 20 I now know is x plus 4 times 3x squared plus 14x minus 5. And you can check, but 3x squared plus 14x minus 5 is 3x minus 1 times x plus 5. Okay, let's take a look at one more example of synthetic division. Here, I have 2x cubed minus 17x minus 16 divided by x plus 3. Now, in polynomial long division, you had to watch out for missing terms in both your divisor and your dividend. In synthetic division, my divisor should be a binomial, so I shouldn't have anything missing. But I do have a missing x squared term here, so I need to take that into account. When I write out my synthetic division, my coefficients are 2 and 0 and negative 17 and negative 16. The root of x plus 3 is negative 3. And once again, what am I going to do? Drop, multiply, add, keep doing it until I am done. So I drop the 2. Multiply by negative 3 to get negative 6. Adding 0 and negative 6 will give me negative 6. Multiplying these two gives me 18. Negative 17 and 18 add to give us 1. And negative 3 times 1 gives me negative 3. So what I get then is 19. So again, I have done the division of these two polynomials without having to deal with any long division, just dealing with numbers, multiplying, adding, quite simple operations. Once I have, once again, the quotient here, that was x cubed, so I expect a quadratic right here. This is my remainder, a constant, an x term, and an x squared term. So, this means this quotient is equal to 2x squared minus 6x plus 1 plus, again, I take that remainder and I put it over x plus 3. And again, this 19 would represent what I would get if I substituted my root, negative 3, into this polynomial. And I'll show you that once again. For x equal to negative 3, 2x cubed minus 17x minus 16 gives me 2 times negative 3 cubed minus 17 times negative 3 minus 16, which is 2 times negative 27. The product of negative 17 and negative 3 is positive 51 minus 16. 2 times negative, I should have just written an equal sign here, I'm sorry. 2 times negative 27 is negative 54 plus 51 minus 16. Negative 54 and plus 51 make negative 3. Minus 16 will give me negative 19. And I realize I did something silly over here. I completely forgot a negative sign. Nobody's perfect, but there it is. Okay. So that is the quotient. Obviously, synthetic division, there's much less work to it. It's much more compact than polynomial long division. Why it works is sort of difficult to explain and beyond the scope, really, of Algebra 2. So, we keep that in mind. Now, why we care so much about polynomial division is it gives us more ways of factoring. So, if you will, bear with me for a second. I'm going to flip this over right here. And let's ask, where does this go next? If I tell you that x plus 3 is a factor of some polynomial, and ask you to completely factor this polynomial and give its zeros, well, we can do this. This polynomial right here, I have all my terms, nothing is missing. So I take them, 7 and negative 10 and negative 159 and negative 198. Large numbers, but I promise you this will work. If I have x plus 3, then the root that I must use is negative 3. I drop this down, 7, and I multiply. Remember, drop, multiply, add, multiply, add. 7 times negative 3 is negative 21. Negative 10 and negative 21 give me negative 31. Negative 3 times negative 31 is 93. Negative 159 plus 93 is negative 66. Once again, I multiply. Negative 3 times negative 66 is 198. Okay? So I got no remainder. Again, no remainder means x plus 3 is a factor, which is what I said. What is the rest of this? Well, I have a constant, an x term, and an x squared term. So x plus 3, the quotient of these two gives me 7x squared minus 31x minus 66. So in other words, what I have shown so far is that 7x cubed minus 10x squared minus 159x minus 198 is equal to 7x squared minus 31x minus 66 times x plus 3. So I have partially factored it. Well, I can keep factoring this because this right here is a factorable quadratic. It's a little bit hard because these numbers are large. 7 times negative 66 is negative 462 x squared. And you have to work at this a little bit maybe to get it, but the factors of negative 462 that add up to negative 31 are negative 42 and positive 11. And once I have that, I can group and factor in the normal fashion. 7x times x minus 6 plus 11 times x minus 6. And I can then see I now have my factors. What I have here is 7x plus 11 and x minus 6. So 7x cubed minus 10x squared minus 159x minus 198 factors as 7x plus 11, x minus 6 times x plus 3. So there's my complete factorization. What are my zeros? Well, if you set each factor to 0 and solve, what you will get are negative 11 sevenths, positive 6, and negative 3. Please make sure to clearly indicate your answers as always. Let's take a look at one more of those examples. Asked slightly differently, but the same type of idea, the same type of problem. If I tell you this function right here has one zero, which is 2, and ask you to completely factor and find all of its zeros, well, what I'm going to do is take, again, each of these coefficients, do some synthetic division. So if I have 1, 0 is 2. As we study in polynomials, we know that means that x minus 2 is a factor, which I will use shortly. But let's do the synthetic division. So I have 5 and negative 19 and negative 2 and 76 and negative 72. I put the 2 out there. I was told 2 was the 0, so I'm using that 0. I'm using my root. Don't need to change its sign. The others, the sign changes from solving. And I drop, and I multiply, and I add, and I multiply and add, and multiply, and add, and multiply. And again, I get that 0, which again confirms that it is indeed a factor. So this is my remainder. I've got a constant, an x term, an x squared term, and here I have an x cubed term. So what do I have? I have 5x cubed minus 9x squared minus 20x plus 36. All right, well, this is a polynomial with 4 terms, which means I can try to factor it by grouping. And I think I'm going to get lucky here, and this will factor by grouping. The first pair, the GCF is x squared, leaving me with 5x minus 9. The second pair, the GCF is negative 4, leaving me with 5x minus 9. So what do I have? I have x squared minus 4 times 5x minus 9. So at that point I could solve even if these weren't both factorable, but they are both, or excuse me, x squared minus 4 is factorable. The other is a linear binomial, so I'm done factoring that. I get x plus 2, x minus 2, and 5x minus 9. So I was asked to completely factor f of x and find all of its zeros. So my factorization, f of x was equal to, well, I have here x plus 2. Now, mind you, I already knew x minus 2 was a factor up here, and I got it down here, which actually means I will have x minus 2 squared as a factor. And you can check, this should make sense. If I do x plus 2 times x minus 2 squared times 5x minus 9, that will give me a product of 5x to the 4th, agreeing with what I originally had. And then I can get my zeros. For my zeros, what I should have is, I can see I have negative 2, and I also have 9/5, And from x minus 2 squared, I also have a 0 of 2 with multiplicity 2. I don't need to write the others have multiplicity 1. If you don't state the multiplicity, it's assumed that it's 1. But I have my 4 zeros, so this makes sense. Fourth degree polynomial, a quartic, I expect to have at most 4 zeros. It does have 4 zeros, it's just that 2 has a multiplicity of 2. So I have 1, 2, 3, 4 zeros. Not all are distinct. Hopefully this has helped you to understand synthetic division.